Today's lesson will cover polynomial functions as well as the key components of polynomial functions. At the end of this, you should be able to sketch polynomial functions given minimal information. All right, let's look at vertex versus reference point. Let's make sure we understand this. If we have a minimum here, as in this quadratic, we have a vertex. Our vertex is at 2, 1, and you can see by the equation, you've already been able to pick this out, or 2, -1, I should say. Whereas in this cubic function, we really don't have a vertex, so we call this a reference point. And if we look at our cubic function, our reference point is, again, our HK, our 1, 2. That's a reference point. And then it's important to get a point on either side in order to graph it appropriately. Let's do some exploration. Take out your calculator, and then what you're going to do is graph these functions in your y equals. So you have y1, you can put this function, y2, and y3. Graph them one at a time, and then what you're going to do is identify the zeros or the roots. Identify whether those roots cross the x-axis or just touch but never cross. Then, what is the degree of the function? You should be able to look at your original function and determine the degree. It's a little bit tricky, but see if you can determine what it is. And then look at your graph and count the number of turning points. So go ahead and pause the video and do an exploration on your own. When you come back, we'll have our answers. Okay, here are our graphs graphed. So let's look at our first one. We can see that we have a 0 here at -2, and then we have one here at 0. So hopefully you got those two zeros. And then as far as turning points, notice that we turn here 1, another one here 2, and another one down here 3. So there's actually 3 turning points on this, and we have a degree of 4. How do we calculate 4? Well, we look at the total number of x's. So we have 3 x's here in parentheses plus the 1 on the end. That's 4. All right, let's look at our second equation. Our second equation we need to zoom out for a little bit just so we can see all the turning points. And we can see that we have 1, 2 turning points. We can see our zeros are going to be at 1, and it's a little, or -1 I should say, and it's a little hard to tell this zoomed out, but if I were to click on that point, I can see it's at -1, 0, and then we have another one here, and it's almost not quite showing up exactly, but it's at 4, 0 as well. So I have 2 zeros, I have 2 turning points, but what is my degree? My degree is 3. Now let's go to the last one. Well, this one's going to be a little tough to see. So this is why we have these rules in order to help us identify when we have a graph like this. I am unable to determine where this graph starts, where it ends, because it's just so massive. So let's go back to our table and see if we can figure out what this equation is supposed to look like. Okay, so here's our table, and I've listed in here our zeros, which ones cross, which ones touch. And I don't know if you noticed that, but notice in this case, our x here, our 0 that was at x, it crossed. Then the -2 from here also crossed. If we look at our second function, we had a -1 and a +4 as zeros. The -1 crossed, but the 4 only touched. So what I'm wondering is if you can see any patterns there. Which ones are crossing and which ones are touching? Let's go back and look. So here's our function, the x + 1, x - 4 squared. And notice here we have our -1, it's crossing through there. But our -4, which is our +4 root, only touches. So let's create another equation. Let's create one that has, let's say, x - 1. And let's raise this to the 4th power. We'll hide the other one. Notice that just touches. What if I raise this one to the 3rd power instead? Notice that it actually crosses through our root of +1. What if I raise this to the 6th power? Notice that it once again just touches. So let's create 2. Let's raise this to the second power. Let's create another factor. Let's try x plus 1, let's say. Now notice this is raised to the first power. It's going through, it's crossing right here at -1. But at +1, our other root, it is just touching. Let's do another one. How about x? We'll do x minus 3 this time. Let's raise this to the 4th power. So here's our root at +3 for the x minus 3. And it's to the 4th power. Notice that it's just touching and going up. So what conclusions can we draw about the multiplicity of a factor and whether it's going to cause the function to cross through that factor at the x-axis or just touch and go up? So hopefully if you look at this pattern, if you have an even multiplicity, so the factor x minus 1 is raised to an even power, the second. The factor x minus 3 is also raised to an even power, the 4th. So if we look at these zeros or roots at 1 and 3, the graph touches and then goes back up. If we have an odd multiplicity like x plus 1 is to the 1 power, so our 0 at -1, the graph actually passes through that 0. So we can make a statement that if we have an even multiplicity, our graph will just touch the factor or 0 and then go back up, but never cross, or perhaps go back down if we're below. If we have an odd multiplicity, the graph will actually cross through the x-axis at that root or 0. If we look back at our table then, now we understand why some of our zeros cross and why some of them touch. Now, we understand the degree. We just count the x's. We talked about that. But let's compare it to the number of turning points, because this will be our turning points theorem. Notice that whatever degree we have, so on this bottom one, we have a degree of 5, 6, 7, 8, 9, 10, 11, 12. That's very high, and it was difficult for us to see and evaluate that graph on our small graph. But we know based on this pattern that our number of turning points is actually going to be 11. So let's look at our turning point theorem. If f is a polynomial function of degree n, then f has at most, and think about what you would fill in for that. How many turning points? How could you write that? Well, f has at most n, the degree, minus 1 turning points. So that's how we'll know how many turning points. If you have a polynomial that is degree of 20, you know there's going to be 19 turning points. Okay, so our questions. Are the zeros of a polynomial related to its factors? And now you can say, yes, you have actually looked. We can see these factors are in fact the zeros, so we can answer that question. And how do the exponents in each term in the factored form of the polynomial function affect its graph? Well, now we know that if we have an even exponent, even multiplicity, the graph will touch at that 0 and go back up. If it's an odd exponent or an odd multiplicity, it will cross through. And then number 3, what does the degree of the polynomial function tell you about its end behavior? Well, let's think about it. We've already looked at that. We know that the degree, if it's even, it's going to look more like a line. If it's, and let's go back over here, if it's even, the even one will look more like a quadratic or a bowl. Our end behaviors will be the same, either both going up, both going down. If it's odd, our end behavior is opposite. So one side goes one way, the other side goes the other way. So we know that from previous lessons. Let's go ahead and apply what we know. We're going to write the factored form of a polynomial function that crosses the x-axis at -2 and 5 and then touches at 3. So pause the video and see if you can write out a polynomial function that has this criteria. Okay, what you should have written, we should write the factors first. So we know that there's 3 factors. So we have 1 at x plus 2. We have 1 at x minus 5, and then we have 1 here at x minus 3. So these are our factors, and our zeros will always be the opposites. Now, what degree do we make these? Well, if we have one that crosses at these two, this has to be an odd multiplicity. So we could leave these both as 1, or we could make one be 3, or we could make another one be 5. If this one touches, then it has to be an even multiplicity. So this one has to be 2 or 4 or 6, and I'll just make that 2. Which of the zeros must have a multiplicity greater than 1? Well, let's think about that. We just answered that question. Both of these that cross through can have an odd multiplicity, and one is odd. Well, the next number is 2, and that's even. This one, since it just touches and goes up, has to have an even multiplicity, so it can't be 1, but it can be 2. Can you write another polynomial with the same conditions? We could, right? We could have put a 5 here or any other odd multiplicity. We could have put a 4 here or any other even multiplicity. So there are many ways that we could have sketched out this function to match this criteria or these conditions. Let's look at our last problem of the day. In this one, we want to give a possible polynomial equation for this graph. So the first thing is to look at all of our zeros or our roots. Let's write those out. We know that we have, it looks like this graph goes by ones. So we have x's at -1, 0, 1, 2, and we'll call this one 2.5. Now we can make factors out of these, so we can start to build our function, and we can say that this is x plus 1. This 0 means that we just have an x, right? This is x plus 0 or just x. Then we have one at x minus 1, x minus 2, and x minus 2.5. Now the key is to put multiplicities or exponents up here. Well, let's see. This one passes through, this one passes through, this one passes through, but our 2 does not. Our 2 touches and then goes back down. So this has to be even. So this has to be a 2, a 4, or a 6, or an 8, or any other even exponent. Now here's the problem. I'm going to go ahead and I put my 2 here, but how do I know it's a 2? How do I know it's a 2 and not a 4 or a 6 or an 8? Well, that's where I'm going to look at my turning points. So how many turning points do I have in this graph? Well, we have 1, 2, 3, 4, 5. If I have 5 turning points, then what does my degree have to equal? Well, we know that the degree relates to the turning points because the degree is 1 more than the number of turning points, so our degree has to be 6. If I put a 2 here, do I have degree 6? Let's count. 1, 2, 3, 4, 5, 6. So I'm fine. If, on the other hand, instead of a 2, I had put a 4 here, would this still work? 1, 2, 3, 4, 5, 6, 7, 8. No, it would not have worked. So when you are putting the degrees, when you are putting the multiplicities, the exponents, you need to consider the degree. And to figure out the degree, you need to look at the number of turning points. And this concludes our lesson on polynomial functions. So hopefully at this point, you're able to write a polynomial function given zeros. You're also able to find zeros given a function or graph. You can determine multiplicity. And by determining multiplicity, you can determine the shape or the behavior of your function. You also will understand how end behavior and intercepts work based on the multiplicity, and then determine the number of turning points based on the degree, and vice versa.